No, get the no, it's not rolling.
So David, what's up?
Do you hear about Amanda?
Come on guys, hurry up. We have short period today. It's a 5-minute video. Come on guys, hurry up. Sit down. David, we don't have time for this. Okay, so, today's lesson is about kinematics. Shh.
Daddy, there's no one.
Guys.
What?
So, kinematics. It's the study of motion of an object, so like the position, velocity, and acceleration. What are you looking at me super for? Okay.
Lucky. We
What?
don't have time.
Okay,
For a 5-minute video.
Okay, so, position of an object is the distance it's traveled from a starting point or an origin. And this is going to be measured in meters. Velocity is the rate of change of position, which is actually measured in meters per second. This group isn't working for me, guys. Tomorrow I'm moving you guys somewhere else, okay? So, we have two types of velocity. We have instantaneous and average. David, would you like to explain the two?
Well, average velocity would be like the velocity determined by 2 moments in time, whereas instantaneous velocity would be the velocity at an instant where the change in time approaches 0. So basically a derivative.
Actually that's pretty good. So, let's get to, the kinematic equations. Here we have a simple velocity versus time graph, with a line of slope A, which will be our acceleration. Looking over at these equations, we could say that Vf is equal to V naught plus AT, similar to the equation y equals mx plus b. Where your m, or the slope, is going to be a, your x is going to be your change in time, and your y is going to be Vf. Once we take the integral of this equation, though, we get this new formula, which is actually our first kinematic equation. Delta x is equal to V naught t plus 1/2 AT squared. Both of these equations come in handy with a lot of things, since they are related to each other by integral and derivative.
So, Akito, just to make sure, the integral velocity, or the area under the curve, is position?
Yeah. And the derivative velocity, or the slope of the line, is acceleration.
Cool.
Okay, so, as we all know, projectiles fly in a parabolic-like pattern. Here, looking at this illustration, we see, let's say, a ball that launches up with an initial velocity, goes up, reaches its maximum, and then comes back down with the same speed, except it's in the opposite direction from the first time. And as we can see, we see that this motion, what's funny, is symmetric. So, what is so fun? Not working. Anyway, moving on to energy, we can use energy to derive one of our kinematic equations. So, here we have EI is equal to EF, so we take 1/2 mv squared is equal to mgh plus 1/2 mvf squared. From this we cancel all the m's, and we're left with this equation. After multiplying everything by 2, we get V naught squared is equal to 2gh plus Vf squared. Once we move everything around a little, we get Vf squared is equal to V naught squared plus minus 2gh. Now, this minus is different from our kinematic equation because this g also is a minus, so in the end they end up canceling out. And what we get is Vf squared is equal to V naught squared plus 2ah. Okay, so J. Audie, based on your position versus time graph, tell me everything you can find out just looking at the graph.
Based on the position versus time graph, you can determine the direction of acceleration by looking at the concavity
Not concavity, concavity.
Okay, you can base it on the concavity. Okay, so if it's concave up, the acceleration is positive. If it's concave down, the acceleration is negative. And I'm done.
Give me a second, David. Let me just finish writing in your profile thing. Okay, so based on your velocity versus time graph and all the points on the graph, tell me everything you can figure out from it.
Right, so as we've seen, this is a velocity versus time graph. So we know that at points B and D, the velocity is equal to 0 because it crosses the x-axis. We also can know where the acceleration is 0. At C, we can see that the acceleration is obviously 0 because acceleration is the derivative of velocity.
Okay. What about finding out the distance that the object traveled?
Well, then you would just have to take the integral. Assuming that the particle starts at 0, you would just have to take the integral and add.
So basically, if we were talking from A to C, and let's say this graph was in fact to scale, would the particle be more on the positive side? It would be on the positive side of the origin or on the negative side?
Yeah, it would be on the positive side because the area from under B to C is greater than the area from A to B. Everywhere else it's slowing down.
Okay. Let me just finish writing comments and grade reports on stuff. Okay, David, I think you're done. Thank you.
Cool. Now some final words from Lakitawa.
Kinematics is all around us and surrounds us. We have to do our best to remember kinematics, and don't forget kinematics for things like energy. Kinematics is important. From all of us at Ghetto Student Productions.